Welcome to The Explainer. Today, we are officially arriving at the grand finale. Every single concept in subsea engineering, the foundations, the massive structures, the intricate pipelines, it all eventually comes down to one afternoon on a vessel deck. This is it. This is where all the math, all the structural modeling, and all that complex seabed soil analysis finally hit the water. It's the moment a crew has to execute a precise, absolutely irreversible sequence of steps to safely deploy a multi-ton structure all the way down to the ocean floor. Okay, let's dive right into this, because this really is the ultimate high-stakes operation. I want you to think of marine installation exactly like a rocket launch sequence. You've got discrete stages, telemetry tracking, and an environment that is entirely unforgiving. Every check, every gauge reading, every single stage transition is monitored against an expected trend. But here, instead of going up into the vacuum of space, we're descending through the dynamic, churning ocean surface down to the crushing pressures of the seabed. And just like a rocket launch, there is zero room for error. Get any step wrong, and there is no undo button. Consider this our pre-flight checklist for today. We're going to quickly cover the point of no return, the four-stage sequence, the critical danger zone, connecting the subsea field, and lastly, the final verification. All right, let's hit our first checkpoint, the point of no return, which truly is the ultimate test of subsea engineering. You see, subsea installation is fundamentally irreversible in real time. The crew's main job here is to manage risk at every discrete stage of deployment, simply because each stage has a totally different failure mode. Once a massive multi-ton structure is lifted off that deck and begins its descent, well, there's no pausing physics. The crew can really only monitor the situation and provide a highly controlled response within the sequence exactly as it was originally designed. And the sheer mind-boggling scale we're working with here, it's just incredible. We're talking about suction pile foundations that can be 15 to 20 meters wide and penetrate up to 30 meters into the seabed. Just imagine that for a second. You are parking a massive steel cylinder on a seabed you can't even see, in a current you can't fight, from a surface vessel that's bobbing around with every single wave, and you still need to land this thing within centimeters of a target. Moving right down our checklist, we reach the actual descent. Let's look at the four-stage sequence of getting to the seabed. Installing one of these suction piles is basically a four-act play. It really builds just like a multi-stage rocket separation. It's a continuous, ordered progression. We've got overboarding, self-weight penetration, venting, and finally, pump out. Let's break these down step by step. Act 1 is overboarding. This is the controlled lowering of the structure from the deck, through the air, and right into the water. Now, the absolute critical moment here is passing through the splash zone. This is by far the most exposed stage of the entire sequence because you're dealing with wave-induced dynamic loading. The immense, chaotic forces of the surface waves are literally fighting the vessel's crane. You've got to get this massive steel structure safely submerged without pendulum motions just completely tearing the rigging apart. Act 2 is self-weight penetration. The pile reaches the mudline and, well, gravity just takes over. The hollow steel cylinder passively cuts into the seabed, sinking purely under its own massive weight. It's going to keep cutting down into the mud until the upward resistance of the soil exactly balances out the submerged weight of the pile. This is a totally passive stage. It's governed entirely by the geotechnical mechanics of the local soil. Act 3 is venting, and honestly, this happens concurrently with penetration. Think about pushing an open-bottomed cup down into a bucket of wet sand. The water trapped inside the cup needs somewhere to go as the sand pushes up inside, right? So by opening valves on the top cap of the suction pile, we allow that trapped water to vent right out. If we didn't do this, we'd create a massive pressure lock, and the pile would simply stop sinking. Or worse, the trapped pressure could literally burst or compromise the structure itself. And finally, Act 4, pump out. Gravity can really only take us so far. To get to our final design depth, which remember can be up to 30 meters down, a remotely operated vehicle, an ROV, attaches to the top cap and actively pumps the remaining water out. This creates an internal underpressure, a vacuum, that physically sucks the pile the rest of the way down. But more importantly, this active suction mechanism is exactly what secures the reverse end bearing capacity, or REB, capacity. That REB is what allows the foundation to resist massive vertical uplift during a future hurricane. It works just like trying to pull a fully sealed plunger straight up out of a bucket of water. Which brings us to the absolute most tense part of the sequence. Welcome to the critical danger zone. For literally hours, engineers up on the vessel deck are just glued to a live telemetry feed from that ROV. They aren't just turning on a pump and crossing their fingers hoping for the best. They are constantly cross-referencing penetration depth against embedment pressure and the pump rate. But the single most critical gauge on that screen, the one that can silently spell total disaster, is internal plug heave. So let me put you in the hot seat for a second. You're the installation engineer. Your embedment pressure is rising normally, everything looks good, but suddenly the internal plug heave gauge begins to tick upward unexpectedly. What do? Do you just push through and hope it resolves itself? You stop. You absolutely stop or reduce the pump rate immediately and reassess. Any deviation from the expected trend is a strict hold and assess trigger, because if you power through, sure, you might get the pile flush with the seabed, and it might look perfectly installed on the ROV cameras, but it's an invisible failure. You will have completely compromised that reverse end bearing capacity, and the terrifying part is, you won't even know it until the very first major storm load rips the foundation right out of the seabed. So, the crucial point here is understanding why this happens. Internal plug heave basically means that the suction differential you're creating with the pump is no longer pulling the heavy steel pile down. Instead, the suction is so strong that it's actually lifting the soil plug up inside the pile, completely destroying the geotechnical structure of the soil. The suction is tearing up the soil rather than aiding penetration, which fatally threatens the holding capacity of the entire foundation. All right, once our foundations are safely embedded, we zoom out to the next phase, connecting the subsea field. We've got to link all these newly placed foundations together, right? And we do that with pipelines. Now, the behavior of a massive steel pipe suspended under tension between a ship and the seabed changes completely depending on how deep the water is. So we've got three main methods. First is S-lay, which uses high tension and a horizontal stinger. It's great for fast deployment in moderate depths. Then there's J-lay, which drops the pipe almost vertically from a massive tower, minimizing tension, which makes it absolutely essential for ultra-deep water. And finally, reel-lay, where continuous pipe is spooled onto a giant drum on shore and then just unspooled at sea. That offers maximum quality control because all the welding is pre-tested on land. Which brings us to the last item on our checklist, bringing this whole explainer full circle: the final verification. Here's what a lot of people actually miss about this entire process. Installation sequencing isn't just some operational procedure you mindlessly follow. It is the final, live checkpoint for every single design assumption made during the entire life of the project. If the foundation design, the reverse end bearing capacity calculations, and the soil data were all spot on, the installation sequence proceeds exactly as monitored. But if any of them were wrong, this installation is exactly where that error becomes undeniably visible, in real time, with an entire fleet of vessels standing by at massive daily rates. Ultimately, it's the ultimate real-time exam. That real-time data record from the pump-out is what proves, after the fact, that the foundation is actually fit for the field's full operating life. So the next time you think about offshore energy, ask yourself this: when the physics literally cannot be paused, will your live telemetry confirm that your engineering can survive the next major hurricane? Thanks so much for joining me on this explainer. I really hope this deep dive brought the incredible stakes of subsea installation right to the surface for you.